This week, we'll talk about aversive stimuli in general, how they affect escape and avoidance responding, and how they function as punishers. First off, what is an aversive stimulus? How would you define the term aversive? I'll give you a hint. The definition must be based on the effect of the stimulus on behavior. From Iverson and Littell's text, aversive stimuli are commonly deemed noxious or annoying, but those terms don't really mean anything in a vacuum. How do you know something is annoying? Because you avoid it or act to escape it. That just traces back to defining aversive based on the effects on behavior. What do you think is the most commonly used aversive stimulus in basic research? It's shock. Shock is an unconditioned punisher, and it is easily controlled and can be delivered in discrete quote-unquote doses, and it doesn't cause permanent harm to the organism. However, it's not the only stimulus that has been studied. Some other examples include loud noises, bright lights, cold, wind, and even changes in artificial gravity or changes to air pressure. While all of these stimuli can be aversive, they have different physical effects on organisms, so it's interesting to investigate the thresholds at which they evoke avoidance and escape, and for that matter, how they compete with reinforcement if both are contingent on behavior at the same times. Here's one kind of operant conditioning chamber that has been used to study the effects of shock on behavior. We see a lever and a food hopper on the wall, and the bars of the floor can be electrified. There are some problems with this setup. First of all, the organism can carefully stand on bars that aren't currently electrified, avoiding or escaping the stimulus in an unintended way. Secondly, the intensity of the shock actually experienced by the organism depends on how much physical contact between the organism and bar is occurring at the moment. It's not well controlled at all. Electrodes can prevent these problems. In this case, the way that the shock is delivered is very carefully controlled with consistent contact with the organism's body, and no unintended way for the organism to avoid or escape the shock. This all probably sounds pretty macabre, but remember that the shock is not physically dangerous to the organism. We study the effects of aversive stimuli with non-human animals for the same reason that we'd study any basic principle of behavior with non-human animals. All of these principles have certainly been studied with humans as well. When we talk about aversive control in general, we're talking about both punishment and negative reinforcement. While negative reinforcement does increase the rate of responding in the future, and we think of that as a positive thing when it comes to skill acquisition, we are still controlling that response using aversive stimuli. What is the definition of negative reinforcement? When a behavior is maintained by termination of an aversive stimulus, we call that behavior avoidance if it prevents the aversive stimulus from happening in the first place, and escape if it stops the aversive stimulus when it's already present. Per Iverson and Littell's text, as a rule of thumb, stimuli capable of maintaining avoidance usually serve a punishing function as well. If taking something away or preventing the stimulus reinforces a behavior, that same stimulus is probably going to reduce the occurrence of behavior if presented as a consequence. So, what makes a stimulus aversive? How can they come to have that effect on behavior? One case is simply unconditioned aversive stimuli. Why do you think we are born sensitive to these stimuli? And what are some other ways that stimuli can become aversive? In basic research, escape and avoidance has historically been studied based on the effects of the aversive stimuli on lever presses by rats. There are some problems with this, though. Aversive stimuli tend to elicit behaviors that are incompatible with the response being studied. Rats tend to flee or freeze when they experience aversive stimuli. If we want to study whether a rat will press a lever maintained by escape from a shock, it's going to be tough if lever pressing is made much less likely by incompatible fleeing and freezing. This problem can be addressed, though. First of all, we can target a different topography of response that isn't disrupted as much by the elicited response. For example, simply moving to a different area of the operant conditioning chamber. We can also study responding under the control of conditioned aversive stimuli that have been paired with shock. the conditioned aversive stimuli won't elicit as strong of a reaction, if any at all. Now let's talk more about the responses that are maintained by negative reinforcement. First, describe escape-maintained responses. Avoidance is a little more complex. Avoidance happens before an aversive event occurs. How the heck does that work? Well, it does require that the aversive event has been experienced in the past. If that aversive event occurs consistently, whether on a time schedule or in association with other observable environmental stimuli, and if a response in the past has delayed or prevented that aversive event from happening in those contexts, that delay or prevention is what is hypothesized to maintain avoidance. So, we call it escape if a response terminates an aversive stimulus, and avoidance if the response delays or prevents the aversive stimulus. Here's an example. A while back, my significant other got into the car with me and tipped over my huge cup of iced tea. I engaged in the behavior of brushing the ice off my lap and using napkins to dry up. What was my behavior likely maintained by? For a long time after that event, every time my significant other got into the car with me, he carefully held his hand on my iced tea in the cup holder. What was his behavior likely maintained by? Here's another cool point. After a while, he stopped engaging in that behavior. He hadn't contacted the aversive stimulus in so long, he had avoided it for so long, that it no longer controlled his behavior. Avoidance only continues to occur long-term if the aversive stimulus is intermittently contacted. There are a couple of different hypotheses about why avoidance happens, why and how it's maintained over time. First, Sidman avoidance. In this experimental setup, each response increases the delay to an upcoming shock. So if the rat continues to press the lever, it can avoid the shock indefinitely. Or, as quoted in Iverson and Littau's text, steady responding can create extended shock-free periods by repeatedly delaying the aversive event. In Sidman's experiments on this topic, no antecedent stimuli were paired with the schedule of shocks, so avoidance, if it occurred, was unsignaled or undiscriminated. At least that's what it was called. It's certainly possible that the passage of time on that schedule came to have stimulus control over the avoidance response. What we tend to see with this setup is a scallop of responding similar to what we see on an FI schedule. As time goes on, as the shock time comes closer and closer, rate of response increases. However, since an aversive stimulus must be experienced in order for avoidance to continue to occur long-term, responding eventually slows down and stops again. Then, a shock is experienced, and rate of response right after the shock occurs is low. And it accelerates again as the next shock approaches. Here's a diagram of the postponement schedule of Sidman avoidance. Let's first look at what happens if no response occurs and the shock is contacted. You start at the top left. A timer starts, counting down in seconds until the shock. If no response occurs, we go down the flowchart where it says no. The timer runs out to 0 seconds. The shock happens, and the timer restarts back at the top. The time between the clock starting and the shock occurring is the shock-shock interval. Now, what if an avoidance response occurs? We'll again start at the top left. A timer starts, counting down in seconds until the shock. If a response occurs, we go to the right where it says yes. The timer increases to in 2 seconds. Again, if a response occurs, the timer resets, postponing the shock. The length of the time interval when it's reset is the response shock interval. But remember, avoidance doesn't maintain long-term unless the shock is sometimes experienced. Eventually, responding on the right will stop or slow down enough, and the second timer will run out, starting the flowchart all over again. Here's an example of a rat's responding during this kind of schedule. Each data series represents a different shock-shock interval. a different length of time between shocks if no responses occurred. Along the x-axis, we see the response shock interval, how much each response will delay the shock. Let's start on the left of the graph, where we see the data series represented by triangles and the dotted line. In this case, the time between shocks is 2.5 seconds. If each response delays the shock further by 2.5 seconds, we see an average rate of responding of 26.5 per minute, just enough to completely prevent the shocks. Following the same data series, if the shock occurs every 2.5 seconds and every response delays it by an additional 10 seconds, we see an average rate of response of 11 per minute. The rat doesn't need to respond as often to completely avoid the shock. As the response shock interval increases, rate of responding decreases. But what if the shock interval is longer? The open squares with a solid line represent a 30-second interval between shocks. With a response shock interval of 15 seconds, if the organism responds, the shock will actually come sooner. So you can see that the rate of response is pretty low, only once every other minute or so. It may be worth responding right at the end of a 30-second interval in order to postpone the shock, but then you're on the right side of that flowchart where now the shock will come more often if you keep responding. If the response shock interval is 30 seconds though, now responding can delay the shock indefinitely if it keeps happening, with no penalty. So, rate of response increases to just over 2 per minute. And, as with the other data series, as the response shock interval increases from there, rate of response decreases simply because it's more efficient. That was Sidman avoidance with a shock postponement schedule. Here's another way of investigating aversive control, the frequency reduction schedule. In this case, shocks are not completely removed or avoided, so what would maintain responding? In this experimental setup, there are two ongoing time schedules. The high-rate shock delivery schedule is on by default at the start of the experiment. So let's say that shocks are happening every 5 seconds. Then, if a response occurs, the lower rate schedule begins. Now, shocks will only happen every 10 seconds. That schedule remains on for a set period of time, regardless of what the organism does, and then the higher rate schedule begins again. Research has shown that this model is effective in maintaining quote-unquote avoidance responding, even though the responding doesn't actually completely prevent the shocks. It only reduces the frequency of the shocks, and that in and of itself is enough to act as negative reinforcement. On to punishment, but to review, what is an aversive stimulus? Again, how we define stimuli is based on their effect on behavior. In this case, aversive control refers to both punishment and negative reinforcement. Aversive stimuli increase the rate of behavior in the future if they're removed contingent on the behavior, and decrease the rate of behavior in the future if they are presented contingent on behavior. Remember, per Iverson and Littell, as a rule of thumb, stimuli capable of maintaining avoidance usually serve a punishing function as well. However, what are some of the reasons that aversive stimuli can cease to punish behavior, or at least become less effective? The effectiveness of punishment also depends on competing schedule of reinforcement that are contingent upon the same behavior, motivating operations evoking the behavior, the magnitude and consistency of delivery of the aversive stimulus, habituation to the aversive stimulus, and other variables. Here's a set of cumulative records showing the effects of contingent aversive stimulation on behavior that was also reinforced by food at the same time. At the top left, steady-state responding was achieved with the response being reinforced by food on a variable interval 1-minute schedule. Then, at the phase change, 10 volts of shock were delivered contingent on every response. You can see that responding immediately decreased in rate, but remember, the response is still being reinforced by food. So by the end of the first day, responding was pretty much back to baseline levels despite the shock. At the very start of the second and third day, there was initially a very slight dip in rate of responding, but it quickly accelerated again. Then, in the next row, steady state responding was again achieved with both food and 10 volts of shock contingent on behavior. When 20 volts were delivered contingent on every response after the phase change, rate decreased and took much longer to get back up to baseline rates, but it did recover by the end of that first day. It took until the 35th day for the shock to have basically no effect on the behavior any longer. Now you try. In the third row, we start out with 20 volts of shock and food contingent on behavior. What happened following the phase change line on day 1? And how would you describe responding on day 2? Finally, the last row. During baseline, responding was followed by both food and 30 volts of shock. What happened on the first day? Note that it's just that one cumulative record line after the phase change, with the arrow pointing to it. And how would you describe responding on the 15th day? On the 30th day? So, as you can see, even if an aversive stimulus is effective in eliminating or greatly reducing the rate of responding, if the target response is also being reinforced, the punishment will not remain effective long term. Let's review a bit more about punishment from material that you covered in previous classes. Firstly, of course, the direct effect of punishment is that it leads to a rapid decrease in future rate of responding. But again, what are some variables that affect how effective punishment is? First, learning history. The longer the behavior has been maintained in an organism's repertoire, the less effective punishment will be now. In addition, the longer the time that an organism has been exposed to that particular punisher, the less effective it will be due to habituation. Next, stimulus control. If a response has occurred in a particular environmental context and been regularly reinforced in that context in the past, and you try to punish the behavior in that context, it will be less effective than if you intervene upon the behavior in novel contexts. As discussed previously, the more powerful the maintaining schedule of reinforcement that is contingent on the target behavior, the less effective punishment will be. This is a slightly different point. If the same reinforcement is available contingent on another behavior that is not being punished, punishment will be more effective. Think back to the idea of a response class hierarchy, remember? Then we have a set of points here related to how effectively punishment is implemented. Punishment should be a sufficiently high magnitude right away, not gradually increased. That would lead to more habituation. The punisher should be delivered immediately contingent on the target behavior and on an FR1 schedule. These variables all affect how likely the aversive stimuli will be to actually suppress responding. I'd like to end with a brief contrast between punishment and reinforcement. You may think of them as exact opposites, but they're simply not. This is reviewed very eloquently in Chapter 12 of Skinner's Science and Human Behavior. A single instance of reinforcement contingent on a response can maintain responding for a long time. Intermittent reinforcement is just as effective as continuous reinforcement, and in fact makes behavior more resistant to extinction. In contrast, intermittent punishment is not very effective at all. Continuous punishment can be, but even then may not completely suppress behavior. Why? Why do you think that behavior is more sensitive to reinforcement than it is to punishment? Aversive stimuli have their place in controlling behavior, but I find it so interesting to consider our, and all organisms' extreme sensitivity to the power of reinforcement.